The webinar for today is about dose area product. Just an ambition with this is to clarify a little bit about the DAP, the DAP meter, and how it works in general, and how RTI, what solutions RTI offer in that field. So first, looking at DAP, what is that? Well, dose area product. It's used as an assessment, or in assessing, one part of assessing radiation risk from X-ray, and in that it looks at not only the dose but the radiation, the total radiation administered to a patient or a subject for X-ray. So in some aspects it gives another angle, another view of the radiation risks that a patient is subjected to in this area. It doesn't increase the dose or the risk necessarily, but it gives another view of it in the assessment of radiation risk. The definition is the absorbed dose multiplied by the area that is irradiated. And the expression there is in gray square centimeters typically, or the SI unit would be gray square meters. That's the unit. But of course, depending on the radiation levels, you'll see milligray, microgray square centimeters, or even millimeters. So it's but they're interchangeable. But the SI unit is gray square meters. And of course, that's by multiplying the dose with an area, or a square meter area. You'll see also CAP, Kerma air product, which is a related quantity and which is very, and for all practical purposes, equal to DAP. So it's, but it's not absorbed dose. It is the air Kerma product, but the differences are minute and negligible for all practical purposes. So interchangeable. What do you call it? Nomenclature is DAP and CAP. They're practically interchangeable. So, going back and looking at the definition of it, we've got an area which is irradiated. We measure the dose in the center of that field, or that's the definition of it, and multiply that with the beam size, which is the area irradiated, and then in that way we calculate the DAP. That's the dose multiplied by the area. Simple as that. And what happens there? Well, in doing that from a mechanistic point of view, we've got some challenges in identifying the beam limits. What are the limits of the beam, and what is so we can actually trap and catch the beam edges. That's one challenge that we need to overcome. Secondly, of course, is once we have these limits, is measuring the sides accurately. Is it a square, or is it a rectangle, or is it an octagon, or what is the actual shape of the beam? And that is, or the area that is irradiated. That's another challenge. And of course, to get it completely right, we need to know the angle. We need to ensure that the area we're calculating is at a 90-degree angle to the center of the beam that we're measuring. So those are the challenges when looking at DAP from a definition point of view. Okay, so that's one step along the way. The one phenomena of DAP is also that it's independent of distance. Well, put an asterisk there, because we have a caveat there when we need to take into account. But what happens if we look at a distance of d, and where we have the area irradiated, we call that A. So that gives the DAP at this distance is D multiplied by A. So we need you to mute. Raghav, we need you to mute. Okay? So I've muted you. You'll be able to ask questions at the end. All right. So the DAP, first DAP at this level is D multiplied by A, dA. Those are the areas here. What happens if we extend this to twice the distance, the 2D? Well, the area irradiated will of course then be 4A. That's with the phenomena of inverse square law, and that also has effects on the dose. So doubling the distance will divide the dose by 4. So those even themselves out and gives us dA as the DAP value at this distance as well. So the reduction in dose rate caused by an increased distance is compensated for by the larger area. So the DAP value in itself is constant. And we have the same value, the same DAP value, and that's one of the benefits of using DAP as a measurement in radiation technology. Now, this is valid. The asterisk here and the caveat that we have is that this is provided that the beam is inside the active area of a chamber. If we're using an ion chamber, a DAP chamber, this is what we'll get. It will be independent of the distance. And so by using a DAP chamber, which is a smart thing to do, then we don't need to worry about measuring the sides and etc. We can then look at the active area and how to work that. Well, this is, of course, if we have the radiation covering that part of the active area, that's fine. If we cover this much, it is going to give us also a good value. But if the radiation is outside, if it goes outside, if it's not inside the frame of the DAP chamber, of course, we don't know what the radiation is like, because we have radiation outside the DAP chamber which is not accounted for. It's not measured. And in those cases, that's not a valid way of working with a DAP chamber. So that's typically the only thing we need to worry about is keeping the radiation inside the frame of a DAP chamber. If we do that, we don't have to worry too much about keeping the DAP chamber at a certain distance. As long as the radiation is inside the frame, we're good to go. If we look at these two examples, you can see that, okay, if we keep it close to a source, we'll get one DAP value. If we have the same settings, but increase the distance, the radiation situation would look like this. The beam would be slightly bigger at that point, but will have the same value at for these two measurements if the settings are the same in the DAP area. If we move with the same setting on the X-ray console, where the output is the same from the X-ray machine, in this phenomena, well, we'd have a different DAP value than we had here, because radiation is going outside the measurable area of it. So that's what we need to worry about. We don't need to worry too much about the angle because it's as long as all of the beam goes inside the frame. So that's quite a benefit of using a DAP chamber. We have a little bit of a drawback when it comes to looking at the DAP. Well, if we're measuring DAP at two distances like we did before, we get the same DAP value at distance D and at distance 2D, twice the distance. But the dose rates will be very much different. So that's what we need to keep in mind. What are we actually measuring when we're using DAP? It is then the DAP, the dose area product, which is a value quite different from dose alone or dose rate. So we need to worry about that or watch out for that. In some instances, if we're looking at a radiation risk, since you have the same DAP value here in these two sites, in situations or distances, you'll have a higher dose rate, a much higher dose rate here than there, which then represents a higher risk, radiation risk, with a higher dose rate, of course. But that is not caught, and that is not then measured or evaluated with when we're looking at DAP. So that's just something to remember about. And when we're working with the DAP chambers, we need to watch out also for the calibrations, how the DAP chambers are calibrated. There is one way. There's one radiation measuring what we're trapping with the DAP chamber, and then the incident air karma, which is the RTI standard. But there's also another calibration factor for what is transmitted, and which is something different. It's then the incident air karma minus whatever the attenuation we get from the DAP chamber itself. And that calibration is then typically used in built-in DAP chambers, which are built into the X-ray machine, into the collimator, so to measure the produced radiation from an X-ray tube. So that's also something we need to keep in mind when we're comparing values between different DAP chambers. Are we comparing apples with apples? Meaning that are we looking at the same calibration, measuring the same greatness, incident or transmitted air karma? So that's what we need to watch out for. And that's about it when it comes to the basics of the DAP. And what we can do is then look at how does that how is it used in reality? Well, if we look at in radiography and fluoroscopy, many installations already have the DAP chambers built into underneath the collimator, or as part of the collimator, which is typically covered by what do you call it, covers, so that we don't see them directly, like this one for a vascular machine. But they will then be built in and connected to the X-ray system itself, feeding back the DAP data, so that can be then integrated into the PACS system to keep track of patient doses along the way. Of course, these then would have a calibration of transmitted air karma, so they keep track of what comes out of the complete collimator package, of which the DAP chamber is a part. So they would have calibration corresponding to the transmitted, whatever comes out of the DAP chamber. That's what it's measuring. The dose, the DAP value that reaches the patient. So from our point of view, this may be something then that we could verify and check against to calibrate and verify the output of a DAP chamber like this. And of course, we could do it in tandem or work it with the dose probe and looking at the beam size. So there are different ways of doing it. So that's two examples of it. We also can look at dental, which is becoming more and more interesting when they're looking at the quality assessment for dental machines. And it's becoming a standard now to measure the DAP as a part of the QA procedure of panoramic and CBCT dental machines. And in that case, it's just keeping it, mounting the DAP chamber onto the tube somehow. Most situations are using it with surgical tape and keeping it in place, mounting it on the tube side. This is an interesting where you have a plastic bag and using and taping it in place, and that's fine. Of course, for these kind of applications in dental, it could be useful, not necessarily to have, I think this is a larger one, this is like 147 size. This could be used for these kind of applications. We could use a smaller one because the output here is quite small. We don't need the larger size, which DAP chamber, which could be more challenging to position. But anyway, we don't have any holders here for it. If you see here on the side, there are rails that can be mounted that fit onto the rails into a collimator of this kind. If you're looking at a radiography or fluoroscopy machine, that's a typical standard size where they slide into place. But for dental applications, surgical tape, I think, is the most common way of fixating the DAP chamber. And if we have a smaller DAP chamber, of course, we'll have a better chance of keep putting it in place, in the right place with tape. Of course, this situation here with the cable in front may be a little bit risky, so just we might want to keep the tape out of the way. Then also for intraoral machines, this may be one solution of measuring it, if that's possible. Of course, if you can balance it that way, and if the room allows that could be then one way of doing it. And as you saw, I think you've seen the mail out from the sales department. There are several applications or standards now in place, both from IEC and Sedentex, where DAP chambers are recommended as a part of the QA procedure to verify it. It is a more convenient way. It's an easier way to get reproducible results for constancy checking than CTDI, dental CTDI, which was a hot topic some time ago. And for dental CTDI, I'm just sidetracking a little bit. If there is a requirement for CTDI measurements, we don't have a problem with that. Of course, we can meet that requirement with the CTI in chamber. That's not a problem. But there is challenges with that, big challenges, which have been identified also in many studies. That the one problem is that the movement during the scan is not always symmetrical. and it's not circular, so you don't. There is a difficulty of finding a reproducibility of the measurements due to that fact. The scans are typically less than 360 degrees, so there's not a full rotation of the tube, which again it gives some challenges when it comes to reproducibility. Also, there are some small beams with the cone beam, as opposed to CT, where you may have a fan beam, or if you have a cone beam, you may have the phantom not fully irradiated, the full phantom length, giving quite complex scattering effects inside, and that is also then difficult to to reproduce. And the standard, the CTDI definition is not fulfilled when we're talking in those terms. So that's why it may not be the most effective way or the best way of working with quality assessment in dental. So for those, but if customers insist and they want to measure CTDI in a dental environment, fine, we can supply them with the ion chamber, and that'll be all they need to fulfill that standard. But more and more, like we said, are moving into working with DAP in the quality assessment for dental, panoramic as well as CBCT. All right. Now, for these applications, we then provide the DAP team, which is the main ones is the Cobia and the Piranha dental machines. And with the Cobia dental having been fitted now with an input for external probes, we can use also the DAP chambers with Cobia dental. So we have two ranges of them, the Cobia and the Piranha dental, that they can provide that service. The difference, of course, will be that for panoramic dental, of course, when we need to measure the KV, the detector of the Cobia is a bit too large. So for if there is a KV measurement for panoramic dental, we need to recommend the Piranha dental for panoramic dental. For all the other applications, the Cobia would do the job. For CBCT, KV measurements will be okay, because the detector size the detector will be fully irradiated with the CBCT beam. Those are typically large enough to cover the whole detector area. So that's the only exception that we need to worry about. That for panoramic dental, that's the only exception. For if that is the case, we need to go with the Piranha in there. For the chamber adapters, we've got them in two sizes, as you know, 147 by 147, which is a size that is quite standard for applications in radiography, for instance, or where you have these mounted, the collimator mounted rails, so we can mount like small wings on them that fit into the collimator brackets. For dental, the 86 by 86 is most of the cases does the job. Since we'll be close to the source, the beam is not all that big, so we can survive with the smaller DAP chamber for those applications. which makes that easier to fixate and to position onto the tube itself. If you buy them, you need, of course, a chamber adapter, and as you know, the calibration data for the DAP chambers is stored in the chamber adapter. So if you buy them together, of course, you can get the calibration data programmed into the chamber adapter. If not, you need to, if you're adding the chamber adapter separately, you need the calibration data. You need to store that onto the chamber adapter connector by yourselves using the Detector Manager program. And if you need any help on that, you're welcome to call our support team for that. All right, and of course now with the Cobia Dental here, you have then the possibility to add also a dose probe if you want to measure the dose reproducibility on the detector side using the dose probe if that's necessary. All right, so that's the team. The new addition to the team is the Cobia Dental with the possibility to use external probes. That's the big news. All right, and of course, Ocean, we've added in Ocean also the possibility to measure the cap values, of course. It identifies it if when you make your connection and choose external probe, it will identify a cap calibration if there is one, and give you the choice of measuring with cap or DAP, and of course give you the measurement data according to the calibration you have in the chamber adapter. So with quick check, like this screenshot is from, you'll have that available like with before, the measurement data, waveform, and the grid, like anything else. Of course, they'll be able to work and to develop templates for these applications as well. So that's works as like anything else, and that's connected. All right, we're coming to a summary of it a little bit. We're doing well. It's DAP is a way of measuring all radiation of a beam, not to see what, to measure the full beam and all the complete radiation from an X-ray beam. It's constant with varying distance as long as you capture the complete beam. But that does not say anything about the dose rate, unless you compute it backwards and see what do we have, what is the actual size of the beam, and then divide the DAP value with that, and we get the dose. But the DAP value in itself does not say anything about the dose rate. If we have a smaller chamber, it's suitable for mounting close to the source, like in the dental applications. So that's what we would recommend in that case. Larger chambers is more suitable for rad or fluoro, where you have standard rails that you can actually slide them into and do your verification, or you can even tape them onto the collimator and to check the output and to verify the integrated DAP chamber in that case. A smaller DAP chamber may be too small so to capture the complete beam. That's why a larger chamber would be more suitable in this case. And with that, I've come actually to the end of this presentation. I thank you for your attention. With that, we conclude this presentation.